Good morning. It's my pleasure today to introduce our speaker, Professor Howard Chizeck. Professor Chizeck got his bachelor and master degree from Case Western Reserve University and also his PhD degree from MIT in '82. After that, he has been serving as faculty as well as chairman in Case Western Reserve University. In 98, right? 98, he was recruited to come to the University of Washington to become the chairman of my department, of our department, electrical engineering department. And in the past couple of years, he was able to make this department a very strong and high-ranking department. And his research area specifically has been working on control, system control, stochastic control, and also related to a lot of medical and biomedical, biological type of application. And recently, with his research effort, he and some other faculty was able to attract this National Science Foundation ERC Center related to the neuron engineering. And Professor Chizeck is a fellow of IEEE and also a fellow of American Institute of Medical and Biological
engineering.
Right, engineering. Okay. So let's welcome Professor Chizeck.
So good morning. I actually recognize most of you from classes. So talk about something entirely different, haptic rendering from non-contact sensors. So touch is a big deal. When we want to interact with our world, usually we look at things, and after we've looked at them, you reach out and touch it. Grab it, see what it feels like. Does it squish? Is it rough? You know, and if you've had small children, you know the next thing is you taste it. Okay. At any rate, touch is deeply ingrained in our culture. In fact, when Ma Bell, may she rest in peace, was the one monopoly and telephones looked like that, reaching out and touching someone was a major campaign for like 10 years for advertisement. And rather than touch someone, you could touch something. So when some of you were small children, E.T. came out, and one of the key moments is the great touch that happens. Okay. Well, now there's an interest in touching things when we're not really there. Okay. Now that you all are carrying some device and you're busy tapping on it, some of you, we are not always in the physical present. We're in a virtual world, or we're interacting with people, with machines, with games that are far away. But what we don't have right now is a sense of touch as part of that human-computer interaction. And that's what this is really about. So there's a field called haptics. What's this word haptic having to do with a sense of touch or tactile? It could be force feedback, pushing on something, but it could also be things like texture and heat and vibration. Sensing the shape, and which is what we're doing here, but maybe also softness and texture of an object. When we do it by hand, we've got all this wonderful signal processing and network and sensors to do that. And for our kinesthetic sensory system, we're actually touching objects and seeing if they're hard and where their shape is. What is that responding to? It's responding to the spatial and temporal, time-varying distribution of forces on our fingers and on our hand. So if we want to bring a sense of touch, somehow we have to have a device, a mechanical device or a glove or something that's going to push on our fingers and our hand. Okay, that's the signal that we're built to receive for touch. And there are these things called haptic interfaces and devices, and if you're a gamer, you've seen some of them. They basically are little motor thingies that push back on you or get stiff, resist your motion, and they essentially let you touch or feel or manipulate something somewhere else by feeling what's going on. So if you if you've seen the haptic gloves in some of the gaming devices or joysticks that push back on you for some of the games. This is a field in its infancy. Now, haptic rendering is, roughly speaking, the process of displaying somehow on your force display device, on your mechanical thing, the feel, if you like, of virtual objects. Something that's living in a computer space, something that's living in a game or on a screen or in a piece of software. Okay. And in this work, the virtual environment that we're interested in, it's taking images of physical objects that are obtained from a camera that gives you not only video but depth information. And the new low-cost version of that is the Microsoft Xbox Kinect. So the idea is we'll have some physical objects here. The Kinect will stare at it. Okay, so the Kinect actually broadcasts out infrared in a pattern, and it's got a little receiver and interprets it. And it will assign depth information as well as regular video camera and update that 30 frames per second. And that is the information that we hack out of the front end of the Kinect before all of the wonderful proprietary stuff Microsoft has to recognize limbs and things. We just take that image and put that into the virtual world. And that's the thing that we want to get a sense of touch of. Okay. In other words, if I could get a camera with the right equipment and put it up on a bridge that needs repaired, maybe I could touch and feel if it needs repaired. Or if I'm underwater using sonar and a different kind of camera, maybe I could put my fingers through the mud and the dirty water and feel a mine that needs to be diffused. Or I could, for our motivating application, be interested in robotic surgery, where the surgeon is going in through some tiny small holes into a person's body, and they're remotely have some joystick things to do suturing and cutting and such, but with no sense of touch back. And what we'd like to do is perhaps recognize something that the surgeon shouldn't cut and push back, prevent that from happening, make a no-cut zone. Okay. So it's remote touching. That's what we're interested in. Now, the thing is, we want to do this in real time. The idea of haptic rendering is old, but usually it's very computationally intense. We'd like to not only do it in real time, but with moving objects. Not a fixed scene, you know, not like here, touch the sculpture, but it's made of stone and it doesn't move. Instead, we want to track moving objects, like in a game, or a beating heart. Okay. Now, the Kinect camera, as I said, will give us a depth value for each video pixel, essentially, and we can build these depth values into a thing called a point cloud. That's just a collection of information of depth. The Kinect is doing this for us at 30 hertz. And it's pretty cool. For $150, you can buy a depth camera that gives you video and depth information. Okay, so here's the Kinect. Okay, we're going to have this streamed point cloud information that's been constructed by it. So, you know, it's out here broadcasting infrared with a certain pattern, certain structured light, and then it interprets that and computes the depth by the spread of the infrared dots, gets that information. This guy here is our haptic interface device. This is from Sensible Incorporated. It's an Omni Phantom. They make several of these, but essentially think of it as a fancy multi-jointed mouse that you can push on to move something, but it can push back at you. So sort of like a two-way pen type mouse. Okay. Using these two things and the algorithm that I'll talk about, you can touch an object when it's visualized in the point cloud as it moves. So that's where we're getting to. Okay. So if you know about haptics, there's a thing called the haptic interface point. I'm basically, you know, I've got my tool and I've got an interface point, right? And there's a technique for building a little zone around it, a proxy, and thinking about how that proxy interacts with the physical world. and computing contact force when it's in contact. And traditionally, this was done for telerobotics when you were moving an object that had lots and lots of contact sensors. So you could actually measure forces, or you could measure joints and compute forces. Okay. But we don't have that. We got a bunch of points. We have a point cloud. And these points, let's say they're a surface, and there's our haptic interface and this proxy around it. And the question is, what happens when we come up to, make contact with, possibly go through the object that's represented in point clouds? Now let me start by saying we don't want to go through objects. Okay? If I'm sort of feeling my hand here remotely with my haptic interface point, it's unnerving if it goes through the hand and comes out the other end. So we don't want to go through things. On the other hand, there's a certain density of the points we're getting from the Kinect. There's holes between them. So we might go through. And if this hand moves quickly enough, whoops, goes through. And on top of that, if there's a shadow, if the Kinect is here where my eyes are, and I come in and I'm in the shadow and I can't see, I'll go through. So one of the design goals here is to build something so that the sort of token of our virtual command, the haptic interface point, doesn't go through the objects. It feels them, we get pushed back when we hit them, but we don't pop through. Okay. So at the outset, let me say that if the points are not dense enough or you move the object fast enough, you will go through. So we want to avoid that, we want to mitigate that. At the same time, we want to do this on something like a i5 or an i7 or a Mac, a commercially available laptop. We don't really want a we do want a supercomputer, but we don't have a supercomputer. Okay. So traditionally, you've got a proxy, and when you make contact, you compute a normal force. But in the work that I'm going to present, which I see Frederick Ryden there, the graduate student who dreamed the majority of this up, we're going to have a different kind of proxy. So you see like 3 washers here. This is the 2-dimensional case. There's sort of an outer region, a gray middle sort of ring, and then a center one. Okay. And these 3 regions are used to tell the algorithm what to do and what situation you're in terms of the location of the haptic interface and the virtual object. Okay. You're either in free motion, that's pretty simple, you haven't touched it. You're in contact, or you're kind of digging in. Okay, we needed a term for this, and so the entrenching tool that if you've got one from War Surplus, so we used entrenchment. So it's digging into the point cloud. So this region here is the one that we're going to use to compute that surface normal force. That's the force that gets sent back to the user with a haptic interface device. It's really outside the proxy. Okay. This one here and that one there, we'll talk about for a moment. Okay, so let's talk about this guy. That's when you're in contact. So these are dots. These are points. Depth information that's for some object, right? So you've got all these points. Region 2 is our contact region. Okay, now if I make region 2 really, really wide, then I don't have a lot of resolution in contact. If I make it really, really small, I make it hard to do the calculations. Okay, so it influences the sharpness of the contact. The estimation of the surface normal, we take a weighted average of all the vectors that are inside region 3, and we use that to estimate the surface normal. Okay. So, sort of, if you get close enough, those are the points we use to tell you what force to send back to the haptic interface device. A little technical detail, how do you calculate that? Well, you take the haptic interface and you draw right to the center a vector and you throw in a spring constant. There needs to be a spring constant. You need, otherwise, basically it's not stable. So let's say our proxy is moving in 3 space now. Well, then occasionally we could get dots in region 1. We don't want dots in region 1. That's not good. Okay. All right, so let's go through a little bit of animation and the idea here. Here's my haptic interface point. Here's some, I don't know, surface of a book that the Kinect is seeing and giving me dots. Here's my proxy. Okay, my algorithm wants to move the proxy so that it's next to the haptic interface point. And if the haptic interface point moves to the surface, I have to do the right thing. Okay, so we'll move this guy to there in small steps. How do we do that? Take a vector from the center of the proxy to the center of the hip and move a tiny step. How big a step? Oh, that depends. That's a computational issue. That's an accuracy issue. It's a resolution issue. Okay, now it's moved. Do it again. Up, they're on top of each other. Great. Okay, so now, if I'm over here with that haptic interface device and I move it, the green dot should move and the proxy should move with it. Unless I move really fast. Okay, suppose the proxy is in contact. Then we're going to estimate the surface normal and project it and move 1 step. So here's the situation here. So again, there's my haptic interface point, there's my surface, and there's my proxy. I'll compute these normals and I'll move, and eventually I'll get it to where I want it to be, just above. This is sort of a 2-dimensional slice here. So basically, I'm making this virtual proxy thing track wherever the person is moving the haptic interface point. And why do I want to make it track? Because when it gets to an object, I want to compute a force and send it back to that mechanical device. Okay. So one more time, there's like 3 worlds here, right? There's a physical world where the Kinect is looking at the object. There's a physical world over here where I'm, moving this joystick thing, and then there's a virtual world in between, where the image of the object's thrown in there, we do the calculation, we generate forces and send it back. Okay. The entrenched case, this is great, everything's fine, but I move something. I move the object, the real physical object, and now there's a dot inside the center region. I don't want that. Right? If I keep having that, I'm going to pop right through to the other side. So I want to make sure that my proxy doesn't pop through, even though it's moving. So what we'll do is we'll estimate the surface normal, we'll move in that direction. Uh-oh. We've lost a overloaded my machine. Have to get the department to buy me a new machine. Okay, so we'll just go down to the next one. What you'll eventually get is you will move it, but something's wrong with my software there. All right, let's try this instead. So this is a simulation tool early on for the 2-dimensional case where, let's see if I can make this work. Oh, how embarrassing. Okay. There we go. Media unavailable? No, there we go. Okay. So we're moving. Okay. The haptic interface point was put on the wrong side of the surface, so the proxy stayed on the right side. Okay, and right when it's bouncing on the bottom there, the best it can do is just be right above it normal. Here's another shape. This is a curvy shape. This is harder. And you see if I move the haptic interface point on the wrong side, if I move the haptic interface to push on the book, okay, it stays on the outside and pushes back on me. Okay. So now I'm ready to play with software, right? Once I know where these objects are and can push back, now I can do things like not let the display go inside the object, push back on it, build a control algorithm that says, oh, you're too close and prevents your robot arm from moving in a surgical tool. Okay. So this is 2 dimensions. Okay. So the next step was to do it in 3 dimensions, which involved doing it in 3 dimensions and seeing what happened. Surprisingly, I mean, it was noisy, but it worked. Okay, so the algorithm is extended to 3 dimensions. Okay, this is about the time that requests for bigger, faster computers began. Okay. So, you know, you've got your Kinect. It gives its RGB data. You've got your algorithm for haptic rendering. You have to visualize it on a screen somewhere. It sends forces to this device. There's a person sitting here. The person moves this haptic interface back. It interacts here, right? So this is the virtual world and a screen to see it. This is the physical world, and this is the physical world. Okay, so let's talk about the Kinect for a minute. So it's a 640 by 480 depth and RGB. So this is what your depth images look like, lots of dots. These blacks are shadows. And then there's a video, and you could throw the 2 on top of each other. And if you have 600 by 180 points, 30 hertz, 9 million points per second, please, can I have a faster computer? Okay. So do we need all those points? Okay. Obviously, I don't, right? If I'm going to a certain object and I'm worried about interaction, I really only care about that zone. For the moment, I can sort of ignore the others. And so, you know, if we take an area and we define an area, I am told that something on the order of 400 time improvement in speed. Of course, it depends on the size of the area and the resolution and the rest of it. Okay. Enough to make it run on a i7 or a whatever Mac you just bought. Okay. You want to do more, you're going to need faster processor. But you can do some suggestive things here. Okay, so as I said, the motivation is robotic surgery, but the motivation could be anything where you want to interact and touch at a distance. Okay. That could involve having a control loop to physically modify the physical world, but that's a separate thing. Okay. But you could use this haptic information to inform your device that's sending commands. Okay. So we shall see if some video works here. If not, I'm in trouble. Okay. So you see said student, 2 objects, 2 funny-looking soccer balls. He's got the haptic interface is that point, you got that red dot. He's moving things around, do a little rotation, and he can't knock it into the stable ball. Now the ball's not moving. Okay, so that's not too bad. It's not. Okay. And let's see what he does next. Okay, so now this is like, can you feel my hand? Okay, so he's going to feel his hand. And you can actually feel the edge of a dollar coin with this. That's about the resolution right now. And now you can't hardly see it, but as he moves his hand up, the command source in the corner there, let me see if I can rewind just a little here. Okay, as he moves his hand up, watch the haptic interface device in the lower right-hand corner. So we'll come back here now. And as he lifts his hand up, you see it moves by itself. He's not moving it. That's the remote device, the image of that, pushing against the haptic interface and then coming back as a force on the mechanical device. Okay. So there's some look at some different surfaces here, which is kind of neat. Okay. Now, you don't get a sense of touch from this. If you want to feel soft and hard, you're going to need something like ultrasound. or sonar, where you can get touch information. But what you can do then is play games, right? And I think coming up here, you'll see the haptic interface device is also in the image, so you can see it bouncing around as you do it. And if he moves it too fast, it'll fall through, but we probably didn't put that in there. You can have it there you can see he's moving his hand on the haptic interface device in the background, and then you can see the red dot, which you now can't see probably there. And against the blue, it's easier. It looks better on my screen. So you can lift the thing up, and you can play around with it, and you can move it. Okay. So where do we want to go with this? I'll let this go for a bit here. Where do we want to go with this thing? Well, I talked about robotic surgery, so let me briefly give you the situation. The surgeon is removing an organ. Say it's a transplant. The organ has all kinds of vasculature, all kinds of blood supply. Right? You'd like to cut those and seal them and keep them. And then when you put in a replacement organ, do some reattachment. Okay? But the surgeon is working remotely. Let's say it's a gallbladder operation, and working remotely, not replacing a gallbladder, but working remotely through two holes, no sense of touch, looking at a video screen or a 3D video screen. Okay. So what we want to do is recognize objects in a certain zone, confine the image from that. Now, we aren't going to use a Kinect, obviously. This will be specialty implanted cameras, right, that give us the same information. But then help the surgeon in one of two ways. Either compute pathways to move the tool along, so if you're there moving your surgical control device, you can feel the path you should follow based on the imagery, or just put force fields around things. Don't cut that vein, right? Now, actually, you're allowed to cut the vein, but you'll have to push hard to do it. Okay? So one of the two aircraft makers does that, right? You can fly it in an impossible situation, but you have to really want to. Okay. The other major aircraft maker doesn't let you, even if you'll crash. So having these things, these are called virtual fixtures. Basically, you're defining fixtures, spaces in the virtual world that restrict your motion or guide your motion in the true physical world, but it's there virtually and you get feedback about it. So that's sort of where we're going and why this thing belongs to the general area of robotic surgery. Okay. But it also belongs to any other area where you want to remotely touch things. Okay. Now, what other applications? Obviously gaming. Okay. Probably any other application where a sense of touch would be useful at a distance. You can use your imagination on what you might come up with that. Okay. Certainly inspection in difficult conditions, underwater, high temperature, space, radioactive areas. Anything where you have visual information and a sense of touch might be useful. Okay. What's missing in all of this? Well, we'd really like a $150 glove you could put on to get all this. We have the $150 Kinect now, but the gloves are expensive and don't work very well yet. But there's ongoing work doing that. NASA's funding some, and some game companies are funding some at the other end. So better physical devices to push on you and give you that information, and possibly connecting it indirectly to the nervous system, which is something that's the new center on neural engineering is looking at ways to get sensory information back. This could be a set of sensory information, for example, from a prosthetic, okay, where you use some kind of imaging device to look at objects and use that information. Okay. So I want to first of all credit Frederick, sitting back there, who's sort of been the driving graduate student of this, but the others on the team and key people, Professor Hannaford, I see Blake there, who's got the robot and was here at the beginning of this, and in the discussion where we sort of stimulated or triggered things, kind of like rolling a snowball downhill. Sina Niyokasari. Sina is doing a general exam this afternoon on robotic surgery, so if you're interested, there's another event today. You can go watch the first piece on. Hawkeye King was involved in this. Also, a couple of undergraduates, 2 or 3 or 4 undergraduate researchers who did different software bits. Zach Sigelot in particular. A reference, if you'd like, the most recent one that you could get a hold of is at IROS, which was in September in San Francisco. And so if you'd like to see the paper and connect to there, that's the location for that. And funding from this is from the National Science Foundation Cyber Physical Systems grant. And also SINA is funded by Canada from the NSERC. Okay. So I do want to take questions, but I also promised to do one other thing today. So next quarter, Sina Niyokasari, who was involved in this, is going to be teaching the Haptic Enabled Systems class, which is hands-on with those mechanical phantom devices and others. And so if you're interested in this, I want to put in an advertisement. So this course will be offered next quarter and will sort of cover the whole range of haptics, haptic interfaces and haptic devices. So this isn't included on the lists everywhere, but this can count in the robotics and control sequence. Okay. Okay, at this point, I'm open for questions. Yeah?
That class that you just showed, what are the prerequisites for it?
What are the prerequisites for it?
Yes, Blake?
I'll answer that. It's pretty flexible because we kind of cast a wide net to try and attract students, and in particular, one of the cool things about the class is that we have usually 2 or 3 students every year from the digital arts program, and they make the projects that they're involved in really fun. And but C programming is probably a requirement.
Okay, so I'm going to translate for the video. I just heard that C programming is probably the only core requirement, that there are students from digital arts coming as well as engineering. So you don't have.
The digital arts students actually know C programming.
And the digital arts students know C programming, so you should too. Next question. Yeah?
I've worked with the Kinect before, and there's a lot of sensor noise. In your examples, there seemed to be a lot less sensor noise than when I last used it. Did you do any special filtering or some way to stabilize it?
No. No, it's just in a sense, the haptic render, there is noise, okay? And this is the weakness of the Kinect, right? But first of all, we're tapping off front end. So we're just taking the RGBD matrix, that's it. We're not using anything else, okay? There is noise. You basically have to tune the size of the haptic interface point in the proxy so that the noise isn't an issue, okay? So the lack of noise may be in part a reflection of the graphics and the size of if we made the hip smaller, right, and the proxy smaller, then you would have seen a lot more noise, okay? Your alternative is to spend a couple orders of magnitude more and get a better depth camera. So okay.
Most likely because of the distance, because the way you set up your Kinect camera is so close to your hand. And I don't know about idiots, when you try the Kinect, how far is the Kinect camera to your body?
Probably farther.
Yeah. Because of this infrared, once the distance is further, then a lot of noise will be created.
Yeah, there's also, you can't get too close, and you can't get too far away, and you can't have anything that's an infrared source in the same approximate wavelength. If it's a shiny object, you have problems. If it absorbs IR, you have problems. Interestingly, if you put 2 Kinects in the same room, you get some interesting interference, and there's a student, Nicholas Gustafson, is looking at that right now, and it's actually possible to undo a lot of the problems. But you know, the Kinect was not optimized to be a scientific tool. On the other hand, it's a great enabler for research because it is so low cost and lets you try things out. Okay? So the end product that might be used in a surgical robotic system won't be a Kinect, right? It'll be some other small implantable cameras that are being designed. Okay, but a lot of the basic principles can be tested outside because of it. Okay. Quiet room. Another question? Yeah.
So you mentioned underwater and high radiation applications. Seems like that would interfere with the chemistry.
Well, you're not going to use a Kinect underwater. You're going to use sonar, right? And maybe if you can broadcast it out, you know, up to surface, you could have some video, not in dirty water. Okay. So, but what happens if it's high resolution sonar? You change the frame rate, but other than that, you could still generate point clouds. Okay. Anything you can generate point clouds from. So, could be ultrasound, it could be sonar, it could be, you know, generated from 2D images and created 3D approximation. Okay. Other questions? Okay. In that case, it's early, but I have to go teach another class online across the campus, so thank you very much.